Actually, some of you can move to this side, okay? Because you can see perhaps better here. Okay? Huh? You can see that side. Oh, okay. So our next speaker is Professor Nicolas Gisin from University of Geneva, Switzerland. Actually, we are honored to have him as a speaker. To
Hmm. Can't hear anything now. I can't hear anything. Are you speaking now? No, I don't hear anything. Qu'est-ce qui se passe là? Is something going on? I cannot hear anything. Can you hear me? Can you see me? Is there something going on?
Yes, sir. Hello.
Now I can hear something.
oh, okay, okay, sure, sure. Okay, so our next speaker is Professor Nicolas Gisin from University of Geneva, Switzerland. And we are quite honored to have him as a speaker to celebrate the International Year of Quantum Science and Technology and World Quantum Day at Secure, Center for Quantum Engineering for Research and Education. Okay, and Secure is one of the centers of TCG Crest. So Professor Jisa considers himself to be a quantum engineer, but he has done work in the very philosophical and foundational aspects of science in general. He is a recipient of first John Bell Prize for research in fundamental issues of quantum mechanics. He is also a recipient of the highest Swiss Science Prize. So he completed his PhD in physics from University of Geneva. Then he spent some time in the telecom industry before joining the group of applied physics at University of Geneva. So Professor Gisin has done work on the foundation of quantum mechanics, and his talk is today related to that. And he considers this to be his hobby. Okay, but his real interest is in quantum cryptography and long distance communication. He is also co-founder of a company, ID Quantique, and this company was perhaps the first company to market quantum cryptographic systems. So we are very happy to have him as a speaker, and he is going to tell us about beyond Bell inequality. So Professor Jason.
Okay, thank you very much. It's a pleasure to be kind of in India, although of course I'm physically in Geneva. Est-ce que ça marche le truc? Okay, like that. Yeah, so of course it's always nicer to be really in front of the audience and not at a distance and see you very small on the screen. But let's try it like that. So if there's any problem, any question, maybe you can interrupt me, or at the end, I hope we also have time for questions and answers. So my goal is indeed to tell you about not only Bell inequalities. I consider this to be kind of understood and known. I hope indeed you know a bit about Bell inequalities, and to go beyond it. What comes next after Bell inequalities? You know that there was a Nobel Prize awarded at last to let's say works on Bell inequalities, and now what is coming next? And I will mention these 3 points. So the first one will be quantum non-locality, but you'll see with a question mark. What is a question mark within parentheses? The second one is about network non-locality, and the third one about joint measurement. So it's 3 topics, and it's a bit a lot, 3 topics for a single talk. So I will remain a bit high level, let's say, but I hope you will get something out of these 3 topics. So let's start with this quite old picture now. You see the date 97, really old, where we did in Geneva something, so a test of Bell inequalities in what I call the real world lab. So going outside of a quantum optics lab, going into the real world. So you see that the Lake of Geneva here, you see the Alps and all that. Cornavin, that's where we had our source of entangled photons. And it's also the main train station in Geneva. And then we had Alice in a village a bit north of Geneva called Bellevue, and Bob in another village south of Geneva called Bernay. And the B line here is over 10 kilometers. And we did, okay, this experiment. And here is just to show you that this really led to real results. Don't need to go into any details, but it's a real experiment with data coming out. And maybe the first thing to remind ourselves about Bell inequalities and all these quantum correlations, entanglement, and locality, this is truly intellectually fascinating. I mean, if you don't find this intellectually fascinating, you're not in the right audience. And indeed, for instance, one very natural question is, how does nature do it? You know, somehow these things happen, and it's there, and you can test it experimentally, but how does nature do it? So this is the standard question that physicists ask. And indeed, being a quantum engineer, at least part-time quantum engineer, there's another question that I think we should also ask ourselves, namely, what can one do with these entirely new kinds of correlations? You know, if something is really entirely new, and certainly these correlations that violate Bell inequalities is something shocking, entirely new. So something new should be possible to achieve using these new kind of correlations. And actually the answer to the second question came relatively late. Remember, Bell inequalities were first published in 1964. And so one had to wait 1991. Arthur Eckert, who was a student at that time, just a student in Oxford. And so he realized quite intuitively that non-local quantum correlations are cryptographic keys. And once you make this observation, that changes everything. Because now these quantum correlations are no longer just fascinating to physicists, they become also interesting to all the sponsoring agencies worldwide, because cryptography is, of course, a very important topic, has plenty of applications, and then no one can tell you that this is irrelevant. Well, as long as you just do non-locality, this is kind of, at least to the eyes of some people, irrelevant. So let's go back to, can I get rid of this thing that I have here on top of my screen? Okay, now it's going away. So nature is non-local, question mark. So John Bell, he used to say, or in written here, if a hidden variable theory is local, it will not agree with quantum mechanics or with quantum theory. And if it agrees with quantum mechanics, it will not be local. This is what the theorem says, the theorem that we today named John Bell theorem. So that is a very simple, well-stated sentence that really says what there is. There is a tension between hidden variables and locality. So again, physicists say, oh, this is amazing, how can that be? And the computer scientists or the more applied side guys, maybe the quantum engineers, what can we do with that? And indeed, the kind of answer that physicists give to this kind of question is that according to quantum physics, these quantum correlations, they just happen somehow from outside space-time, which is the, let's say, the beginning of all the tension we have with relativity. And what do I mean when I say that these correlations, quantum correlations, happen from outside space-time? I really mean what is written in the two last sentences here, namely that there is no story in space-time that tell us how it happens. You know, when we do physics, we have, of course, equations, computers, and all this kind of thing, but we also need to tell stories. Whenever you... Sorry?
बढ़िया
Sorry? I didn't get it.
Actually, sorry, I mean, there was some interruption.
Okay, no problem. So, there is no story. And usually when we start teaching anything in physics, we start with stories. We tell, I mean, this body is attracting this other body with a certain force and so on and so on. But to tell how this quantum correlation happened, there is no story. At least no story that takes place in space-time. If there is a story, it takes place in Hilbert space. So let's go back. So this is the standard kind of Bell scenario. Test Bell inequalities. You have Alice and Bob that get, Alice will get questions and has to provide outcomes, and the same on Bob's side. And importantly, we don't allow these parties to communicate. So we have some kind of forbidden communication here. We call it no signaling. But what it really means is that no physical object can carry information between Alice and Bob. So you could think this is a kind of huge wall that prevents any communication or any physical object going from Alice to Bob or vice versa. And the standard way to guarantee this absence of communication is by space-like separation. If Alice input-output is space-like separated from Bob's input-output, so that X, for instance, cannot influence B and Y cannot influence A because of space-like separation, then we are kind of happy. However, if you think just in terms of quantum mechanics and Hilbert space quantum mechanics, in a Hilbert space H, there is no c, there is no speed of light. Of course, when you say space-like separation, we mean speed of light. But there is no speed of light in quantum mechanics. So what really quantum mechanics asserts is that nothing can carry information between Alice and Bob. Because when we do the theory, we have the Hilbert space for Alice, the Hilbert space for Bob, but there's nothing going in between them. There might be something going from a source to Alice and a source to Bob, but nothing goes all the way from Alice to Bob, nor from Bob to Alice. So what I want today to suggest as a first possibility to go beyond standard Bell inequalities is to test quantum theory by assuming that there is actually something hidden that propagates, possibly even at a superluminal speed between Alice and Bob. Something is going on behind the scene, as John Bell used to say. So this is really something which most physicists would not consider. However, there is nothing in Hilbert space quantum mechanics that prevents us from thinking that something is going on. That's the way, again, John Bell used to think. But also when we apply the projection postulate, we see, we act here, it projects the state here, but this projection, although it is, let's say, on Alice's side, affects the state on Bob's side, asymmetrically. So let's see, can we do something like that? So let's assume that there's a real influence going from A to B. So Alice gets her measurement settings, something goes behind the scene, and then Bob gets his input. In this way, very obviously, every correlation can be explained. It's like two students that are actually communicating during an exam. They try to do this communication in a hidden way, maybe to cheat, but there is no way to a priori to guarantee that. You should put a wall or put something in between. Now let's suppose we do the following. We ask the two questions at the same time. And we request that they really answer also, provide these A and B outcomes at the same time, as much as possible at the same time. So much that actually there's just no time for this hidden influence to go from Alice to Bob. Even if it would go, let's say, at 10,000 times the speed of light, if the synchronization of such an experiment is good enough, there will be no time for such a communication. And then, if nature is local, we would see that we don't violate Bell inequalities. So we tried these kind of experiments. So we were among the first doing that in this first experiment here on the lower left, you see. But then, since then, there were 3 more groups doing similar experiments. So we had, again, a source somewhere in Geneva. This time, you see that we are essentially oriented east-west. So it's not the same villages. No, it's Satigny and Gisin. doesn't really matter, but it is east-west. And we do our best to synchronize the outcomes, which means these detectors, this here is a detector, this is the other detector. So you see we are using interferometer. So this is not polarization-based, it's something called time beam-based. That doesn't matter. And here again, you have two detectors for the two possible outcomes on Alice's side. And we synchronize everything so that the timing of the detections is as precise as possible. Now we do all that in the Geneva reference frame. And you will say, but this Geneva reference frame is perfectly arbitrary. Why should it be in the Geneva reference frame that we should align everything? You know that according to relativity, synchronizing something in one reference frame doesn't guarantee that it is synchronized in all the other possible reference frames. So here the idea is to exploit really the fact that we are here east-west. So if we are perfectly well aligned here east-west in this Geneva reference frame, then we would also be perfectly well aligned according to any reference frame that moves perpendicular to this east-west axis. So we should also see, so here you see it again, so the east-west, and now the perpendicular plane, this vertical plane that passes through the north and south pole, according to, so any reference frame moving along that axis would also be perfectly well synchronized. Okay, and now we do the experiments during 12 hours, and in 12 hours, Earth is rotating in such a way that this vertical plane is scanning all possible reference frames. So in this way, we do this kind of experiment. So here you see how we collect the data during 6 hours, so 240 minutes. And here you see the visibility of these fringes, and you see these visibilities over 24 hours and even twice. So actually it was done during 48 hours. And you see that consistently, without any change, the visibility is always larger than 1/√2, which is the minimum visibility needed to violate, for instance, the CHSH Bell inequality. So here we see that, at least given the precision of our measurements, there is no sign of loss of non-locality. This quantum correlation seemingly still violates locality. Here we can put some bounds. And you see, so the bound is between 50,000 and 100,000 times the speed of light, essentially the central region. Why do we have this strange behavior on the sides? This is because actually we were not perfectly east-west. There was about 5 degrees off from this east-west orientation. This corresponds to this peak, which is really at 5 degrees, and symmetrically on the other side. So nice. So this is a nice result. It has been reproduced by at least 3 other groups. And so we can say that if a hidden influence is the explanation of this non-local correlation, so if this story, I told you there is no story in space-time, if there would be a story based on this hidden influence, which clearly goes beyond quantum mechanics, then we could say, okay, it would have to go at least, well, something between 50 and 100,000 times the speed of light. And so, well, of course, it could be that the influence simply goes faster or not exist at all. I mean, that we really have non-locality, which is the dominant view among quantum physicists. And obviously, if you have only two-party experiments with just Alice and Bob, just 2 parties, you cannot hope to do better, except that you could put a better bound. These 100,000 times the speed of light, you could maybe improve that one. Now, maybe just very quickly to be transparent, in this paper, this Nature Physics paper, we proved that, and I don't want to go into any detail here, but you should just remember that if you get interested in that, you have to read this paper. It's important that any explanation of hidden influence at finite speed, the finite speed is very important. If it's infinite speed, then the theorem does collapse, but at finite speed, you would always have a scenario. You say it's a complicated scenario with 4 parties, Alice, Bob, Charlie, and Dave. So there would always be a scenario in which the data that you collect, the probability of the outcomes, given the measurement settings, is actually signaling. So this hidden influence cannot remain hidden. It would really one would really be able to use it to communicate at this superluminal speed using only macroscopic measurement settings and macroscopic measurement outcomes. Okay, so what should we do now? So here again, the list of experiments that have been done. And my claim, and that's the first of the three ways beyond Bell inequalities, is that one should, I believe, really improve these experiments. Physics is an experimental science, and it's only by doing experiments that we are really going to learn something. Just doing the mathematics, I will tell a lot about mathematics in a moment, but just doing the mathematics is not enough. We have to do experiments. Of course, such an experiment will only be able to set a lower speed to this hypothetical hidden influence, but I think it makes sense. And so the question is really, which goal should we, the community, set to ourselves? So far, it was the speed of light. In this experiment, we went to something in between 50 and 100,000 times the speed of light. Is that good enough? I don't think so. Because if you see the other natural speeds, the speed of light and the speed of sound, whether it is in air or in some metal, is always something, a ratio of something like 1,000,000, 10 to the power 6. And so if there is a next speed, it is very plausible, not necessary, but plausible, that the next speed may again be, let's say, 6 orders of magnitude faster than the speed of light. So I would say that we should aim in this next experiment to go to 10 to the power 7 times the speed of light. Why 7? Because then I have a bit of a margin. It's not exactly 10 to the 6, it's a bit better. Anyway, if you do the experiment, do it as good as you can. And I think this experiment today is really feasible. See, we did this experiment almost 20 years ago, not quite, but close. Today, you have way better detectors, these superconducting nano wire single photon detectors, SNSPDs. They are just way better than what we had at the time. Here we had just avalanche photodiodes, so this is way better. So you can easily gain a factor of 10. You can also go to longer distances because we have way better sources, and you can have better data analysis, faster data analysis. For instance, one of the things that we had to collect two photon interference fringes, it took about 5 minutes. During these 5 minutes, Earth is rotating. If your data analysis is faster, you can reduce these 5 minutes to maybe 1 minute, and that will also improve your the bound that you are able to put at the end. So I think this is the way to continue Bell inequalities on the experimental side. This is clearly an experimental work. I hope someone, maybe in India, maybe in Europe, I don't know yet, that someone will do that. I would be very happy to see someone working on that. Let's completely change now. Now I move to something different. It's a different topic. It's the second way beyond Bell inequalities. It's called quantum networks. So here you see I have not only Alice and Bob, but I have A, B, C, D. Okay, I have a network. And then in this example, I have, for instance, B and F. They are connected by some source of entanglement. And you see I have a source of entanglement, well, also indicated here. Of course, this is just an example. You can choose any network, and each time you have such a network, you will have these different sources. And the very natural but important assumption that I'm introducing here is that, for instance, this source between Alice and Bob and that source between Dave and Elfie are independent. So assume independent quantum states. But you see, this could be, for instance, powered by some solar energy, and this one maybe is powered by a university professor on his bicycle. So clearly, these two sources of energy are completely independent. It would not be a scientific explanation to claim that the professor and the solar energy are correlated. So they are independent, and then you can imagine also sources for the other sources of energy for the other sources of entanglement. So we make the assumption that they are independent. Very important assumption here. So what can I do when I do that? Well, I can again ask the question, how can I make sure that such a network is really a quantum one and not just a fake one? And the usual way, if we had only Alice and Bob, we would say, oh, let's violate a Bell inequality or at least some entanglement witness. So here what we want to do is to compare that network with a classical network. So where I replace all the sources by a source of shared randomness. No, classical variables, so classical local variables that go from the source to Bob and Charlie. So here the independence is kept, but now this is no longer a quantum, this would be classical local information. So we want to compare that, and if we can prove that some quantum correlations cannot be achieved with these local variables, then we would have proven non-locality of these networks. And you have here a review paper, okay, which is still a good review paper, although it's almost 3 years old now. Maybe I should insist that this view that you have here is really the view as John Bell used to talk about his inequalities. You know, I met John Bell many times in Geneva. He was also in Geneva, and we had several times dinner together and discussions. So let's go back to this elementary view. So John Bell, he was really thinking, okay, it was not Alice and Bob at that time, but you had two parties, and the source was really sending out particles going to Alice and Bob, and the view was that these particles would be carrying in some kind of backpack some local variables lambda, the same lambda going to the left to Alice and to the right to Bob. That's the usual way, and this is exactly what we're also thinking here. Now, each of these sources is locally propagating these variables. However, today, we often have the view of computer scientists, and the computer scientists, we just talk about shared randomness. It's kind of God-given shared randomness. So there is randomness falling from the sky, and Alice and Bob then collect this shared randomness. So as long as you have only two parties, it doesn't change anything here. But clearly, if you have several sources, independent sources, then you don't have a global shared randomness. You have only randomness shared between those parties that are connected to the same source. And this we'll see clearly in this entanglement swapping scenario, which is also called bilocality. So we have one source here, which I call EPR1, another source here, EPR2. And so here the assumption is really that this lambda 1 that the first source sends to Alice and to Bob is independent from the second source that emits variables, local variables lambda 2 to Bob and to Charlie. And this independence really shows up in the fact that when you try to see which distribution can be achieved in this local way, okay, you sum what is the values of lambda 1, lambda 2, and you multiply the probabilities. Multiplying the probabilities, this is exactly what it means to be independent. So lambda 1 and lambda 2 are independent. This one should maybe be a P1 and a P2. You have two probabilities, one for lambda 1 and one probability for lambda 2. And now you have the probability of outcome for Alice. Probability of A, given, of course, her measurement settings, and given the information she gets, lambda 1. For Bob, he gets the measurement setting Y, and he gets both lambda 1 and lambda 2. And Charlie, at the end, his measurement setting and only lambda 2. And because of this product here between these two probabilities of lambda 1 and lambda 2, this is a product. So this makes all the problem non-linear. And for this reason, the set of B-local, so local with two sources, is not a convex set. And not being convex, contrary to what we have in the standard Bell scenarios, makes a huge difference. So that makes the problem way more difficult and also more interesting. And for instance, here, I'm not going into too many details, but here you have an example of a slice of the set of local or B-local correlations. And you see, so this is the set of the B-local, of the boundary of the set of B-local correlations in this two-dimensional slice. And you see that this is not convex. So if you have a point here, it is B-local, here it is B-local, but a straight line the linear convex combination has the majority of its points to be outside that. And because of this non-convexity, you also see that the inequalities that you get in this case, contrary to whatever you get in the standard Bell scenario, are non-linear. You see the square roots, the yx and the ix and iy, they are linear expressions of the probabilities, but when you take not only the absolute value, but also the square roots, and taking the square roots clearly is a nonlinear operation, and so this is a nonlinear inequality. And you also see that, so the dashed here square, this is actually the set of the standard local Bell correlations. So you see, if you have a point which is somewhere here, it is local according to Bell, but according now to this definition with the independence, you get something which is not B-local. So it really changes it enlarges the domain to explore if you have this assumption of independence, which is so natural. So what can I do with that? So let me show you one very beautiful, in my opinion, outcome, maybe the main outcome of this network non-locality. Let's just start with a super simple case where we have only one party, just Alice, let's say, in a d-dimensional complex Hilbert space. Now, obviously, this, everybody knows, is isomorphic to a real Hilbert space of twice the dimension. You know, every complex number has a real and an imaginary part. Trivial. Okay, and now this is also isomorphic to having a real Hilbert space of the same dimension d, tensor product, a two-dimensional real Hilbert space that people often call a rebit or a real bit, whatever, which I here indicate with this green little thing here. Okay, good. Now let's go to a complicated or a bit more complicated scenario, but still with a single source. One single source that communicates quantum or classical variables to Alice, Bob, and Charlie. Again, here you have these complex Hilbert spaces of dimension d1, d2, and d3 for Alice, Bob, and Charlie, respectively. And this is, again, isomorphic to real Hilbert space of dimension d1 plus d2 plus d3, tensor this real bit here. Now there's a problem here, because these real bits, should I give it to Alice, or to Bob, or to Charlie? If I give it to Alice, then Bob and Charlie cannot act on it. So actually, it would mean that the possible operation by Bob and by Charlie are limited to the real operation represented by real operators or real matrices. And the way around that is not so difficult. We go to what we learned from error correction quantum computation. So we're going to say this should be a logical global qubit. So we put a qubit, a physical qubit, to everyone, Alice, Bob, and Charlie, and we define a logical qubit, 0 bar, as the superposition of all the states with an even number of 1. And the 1 is a superposition of all states with an even number of zeros. And now you see that everyone can flip his, let's say, green qubit, the real qubit, and by flipping his qubit, he will flip the logical qubit. So everybody now has access to this global logical qubit. And because of that, you can pretty easily prove that indeed, with n parties connected to only one source, all Bell scenarios can be described using only real numbers. So this is a paper we published quite some time ago, and you see that, okay, everything can be done with real numbers. So apparently at quantum mechanics, where we use complex numbers, because we learned that at school, actually could be also done using only real numbers, as we do for electrodynamics or all these other fields of science. However, what happens now we go to this bilocality network, with two sources? that are independent. Again, think this is solar energy. This is my university professor on his bicycle. So they are independent. So what can you do here? Well, you see, if we say that these ones are independent, that immediately means or implies that the solution I presented before with this logical qubit, which is shared between the different parties, can no longer work, because here Alice is clearly independent of Charlie, because they are only connected to independent sources. So they cannot share an entangled qubit, a real qubit. So at least the way I presented before to make complex quantum mechanics into a real Hilbert space quantum mechanics will no longer work. Now you may say, okay, maybe I need to be a bit more clever and think a bit longer, and I will find another way to make this real. You will not succeed because of this theorem, which says that in this entanglement swapping scenario, actually you need quite a lot of inputs, so 3 inputs on Ali's side and 6 even on Charlie's side. There is some Bell inequality that achieves a maximum value with the standard complex quantum theory, which happens to be 6 times square root of 2, while real quantum theory, so if you limit to real Hilbert spaces, whatever the dimension, you can go to whatever dimension, doesn't matter. This one is limited to 7.66, which is lower than that one. And so you see that with real Hilbert spaces and the assumption of independence of the sources, you will never be able to reproduce the prediction of standard quantum mechanics. So networks with independent sources cannot be described using only real Hilbert spaces. And I think this is really a beautiful result. There were also experiments here. And okay, let me just repeat that physics is beautiful. There's another thing that I don't want to have time to go into any details, but I think it's a nice thing. So just imagine you have now 3 qubits, no, 3 parties, Alice, Bob, and Charlie, and they're all connected by some quantum states, entangled quantum states, but independent. So this one is independent of that one, independent of that one. And the question is now, how can we, and you see also there are no measurement settings. Here is just a fixed measurement on Alice, a fixed measurement on Bob, and a fixed measurement on Charlie. No choice. And nevertheless, this being quantum, we expect that randomness should be coming out. No, there will be outcomes, and the outcomes should be random. How can we prove that? So here, I can show you, where is it? Yeah, here. So here, indeed, the minimum assumption is about source independence. And indeed, with just this source independence, without assuming any inputs, or in particular, no assuming random inputs, since there are no inputs, they are of course not random. There are these 2 papers, not by myself, but these 2 papers that indeed were able to prove the randomness of these outcomes. Let's see, this outcome A, for instance, similar for B and C. So this is beautiful, but we assume that the sources here are fully independent. And the intuition is that one should be able to do better. And so one suggestion from my side to you guys in India doing research, I would bet that if you just assume epsilon independence, which you would have to define, what does it mean, epsilon independence between these sources? But I believe that epsilon independence is sufficient to prove that the outcomes are random. And that would be beautiful in my opinion, because that would prove that you get quantum randomness out of the absolute minimal assumption that the sources are epsilon independent. You know, if they would be not independent at all, if this university professor on his bicycle and the solar energy and everything else is all fully correlated, that's called superdeterminism. And of course, with superdeterminism, you have no randomness. But with a little bit of independence, I believe there is already some quantum randomness. Okay, I move now on to the third and last part of my ways beyond Bell inequality, which I named here joint quantum measurements. Or maybe the subtitle could be understanding entanglement. So I guess many of you had lectures on quantum information, or maybe even on entanglement theory and so on. So you say, oh, I already understand entanglement. Wait a minute. it's clear that after now more than 30 years of quantum information, we know a lot about entanglement between two or more parties, the usual Alice and Bob. This indeed we know quite well. But what do we know about joint measurements? Measurements whose eigenstates or POVM elements are entangled. For instance, if I ask you, cite me names or give me joint measurements, even about 2 qubits. So very simple, just 2 qubits, give me joint measurements. So I guess you will all be able to say, oh yes, there is the famous Bell state measurement. Okay, indeed, Bell state measurement is a joint measurement between 2 qubits. Give me a second one. And okay, now you are 1,000 kilometers away from me, but I bet that most of you would not be able to cite even a second one. Although there are, of course, a continuous infinity of joint measurements, but we don't know them. We have no names, we have no ways of characterizing them. So there is something which is completely missing today in our understanding of joint quantum measurements. So how to start? Now, of course, you have this continuous infinity of joint measurements. How shall we start? Let me suggest one way to start this research. It starts with the following scenario, which is actually named impossible measurements, and it comes from quantum field theory. So it comes from a kind of a distance, but it's not so difficult. Just imagine some space-time. So horizontally is space, vertically is time, as we are used to. And let's suppose we have some source somewhere. Of course, now these are the light cones. So according to quantum field theory, or more simply according to relativity, communication can only go within this light cone. And on the other side, you have a receiver here. And the receiver, I've drawn the past light cone. So the receiver can only get information coming from this past here. But what we are going to do, and this is really due to this Raphael Sorkin, this professor, in the middle, we are going to perform a measurement, but a non-selective measurement. So I just do a measurement. I don't communicate the result of these measurements. But I imagine these measurements will be described the standard way as we describe measurements in quantum physics. So you will not be surprised here. Let me take an example. I want to do the following measurement. Where is that? Here. This is the measurement. You see, the measurement is characterized by its eigenstates. And here I'm thinking of 2 qubits. So 2 qubits, that means a 4-dimensional Hilbert space. So 4 eigenstates. It's a non-degenerate measurement. The first eigenstate is this 2 qubit state 0, 0, tensor 0, tensor 0. The second one is 0, 1. The third one is 1 tensor plus. The state plus is 0 plus 1. And then is 1 minus, minus being 0 minus 1. So we have 4 product states. So very simple states, very just product states. They're not even entangled. But you also see that this is not a product basis. It is what we call a twisted basis. So it's a twisted basis of 2 qubits. Okay, should be easy to measure, isn't it? So let's try. Let's suppose we start with the sender sending out 1 qubit in the state 0, and coming here from the far remote past, also a qubit in state 0. So this measurement here, we implement this measurement characterized by these 4 eigenstates, but it measures it on one of their eigenstates, this first one. So obviously, according to quantum mechanics, what will come out is the state 0, 0. And that means that the receiver here will get the state 0, get a qubit in state 0. Okay, simple. Now let's suppose the sender acts locally, and her action is just the Pauli matrix sigma x, so flipping his qubits. So now, instead of having the state 0, it's the state 1, because you flipped it. Of course, this one has not been affected by that. That doesn't change anything, but now the measurement is done on the state 1, 0. So what will be the outcome? So no outcome here, or outcome with probability 0. This one comes out with probability 1/2, and this one comes out with probability 1/2. So indeed, what you get here, this first one stays in the state 1, and the second one now is half of the time in the state plus and half of the time in the state minus. So it is actually proportional to the identity, or equal to half of the identity. But now it means that the receiver will get something very different. It gets this mixture, plus and minus, mixed with 50-50 probabilities, which he can distinguish, at least probabilistically, from the state 0. So the receiver can notice whether Alice did perform this action, flipping her qubit, or not. And hence there is communication between the sender and the receiver. But remember, the sender and the receiver are space-like separated, and so communication should be, according to relativity, impossible. And so indeed, what Sorkin named impossible measurement, they are impossible because they are signaling. They are allowing to communicate, okay, here faster than the speed of light, and actually also without anything going from the sender to the receiver. So we understand the origin of these impossible measurements. And clearly, where is the problem here? If I go back, I think I have it here. So the problem is not this kind of communication at the speed of light. The problem is really the measurement. Here we assume we do a measurement over this extended space-like region. How can we do a measurement on 2 qubits which are at a certain distance from each other? So this is probably very likely the problem. And this is why this kind of measurement here in the middle is very often called a non-local measurement, or the measurement of a non-local variable. So let's concentrate on that one. Let's assume we have this Alice and Bob. They are at a distance, and we want to perform a certain measurement M. For instance, we would like to implement a Bell state measurement. Now, this is the measurement we all know. So how can I do it if I don't have my 2 qubits at the same location? Well, there is the usual way in quantum information. We take a second pair of qubits that we call an ancilla or a resource, and we put them in some quantum state, some known quantum state. So this is the quantum state phi plus, the fourth of the Bell states, the 0, plus 1, 1. It's one of the Bell states. So now we use that as a resource. And now we do the following. On both sides, locally, I do a Bell state measurement. So this one I can do because this is a local measurement. On Bob's side, here also I do a local Bell state measurement between these 2 qubits. Again, they are local. Here I draw them at a distance, but you can imagine that these two are put together. So these are 2 local measurements. Now, if I do these 2 local measurements here, I get some outcomes, of course. I get, let's say, outcome A, which can be called it's a psi plus, a psi minus, a phi plus, or a phi minus, and the same for Bob. So I get 1 out of 4 possible measurement outcomes on Alice, and similarly on Bob's side. And then I can communicate this classical information to some observer, final observer, but all the quantum to classical transition happens locally on Alice and locally on Bob's side. And if I do that, and I know a bit of quantum information, I know that in this there's almost like a rectangle here. And in this situation, the number of phi's should be even. So if I know whether it was a phi here, there is a phi here, possibly a phi here, then I know whether this one is a phi or a psi. And the same with the plus or minus signs. So at the end, I know the result. So A and B, these classical data, they collectively code for the outcome of my measurement. And if I do that, believe me, it's not very difficult mathematics here. You recover the Born rule. Good, we want these probabilities. That's the usual standard quantum probabilities. This is clearly no signaling because I'm just doing local operations here, And of course, that the final communication of classical communication, I can do it at the speed of light, or I can just do it also even by a snake post. I don't need to communicate fast because everything is already classical here. And so we say that this is now localizable. That's the terminology. It's local because every transition quantum to classical happens local. Good. However, so all this is fine, but notice that this measurement is not what we call an ideal, or usually is often called also a projective measurement. Because indeed, here, if I try to do the measurement again after having collected my result A and B, try it again, I will not get the same result. So these measurements are not ideal in the sense that they are not immediately reproducible. Or in other words, they are not described by the projection postulate. So we get the Bohr rule, but we don't get the projection postulate. Very obviously, this qubit ends up in a maximally mixed state, similar for that one. So this is very far from being projected onto a Bell state. Okay, actually, for the Bell state, I can be a bit more clever and add yet another ancilla or resource. And let's say it's again a phi+ state. And now I do locally the following. I get an outcome here, let's say B, and I can also, okay, suppose this is now 0, 1, 2, 3, just a matter of notations. I can apply the corresponding Pauli matrix here to this local qubit. Similarly here, apply sigma index A here. And again, you need to do the computation, but if that is a simple one, you will notice that this state here, the final state here, is actually in the, so these two qubits are actually in the state corresponding to the outcome of your Bell state measurement that you performed here. So you see that now the Bell state measurement is not only localized, as we have already seen, but it becomes an ideal measurement, well, swapping these two qubits and swapping these two qubits. Good. Now there is an important theorem here, due to these two gentlemen, Popescu-Weidmann, that says that actually the Bell state measurement is the only joint non-local measurement on two qubits that can be measured ideally without leading to this famous signaling problem that I have introduced a few slides ago. So what this means is very important when we think of joint measurements, namely that the Bell state measurement, the one that everyone usually mentions as a joint measurement, is actually not at all a typical joint measurement. It's an exceptional measurement. And so if you want to build your intuition of joint measurements, you should certainly not build your intuition on the Bell state measurement, because this is a very, very peculiar and exceptional measurement. So now we are in a situation which is maybe even worse than a few minutes ago, because we still don't have a second example of a joint measurement, well, except these twisted bases. Moreover, the standard example of a joint measurement is actually a very bad example because it is so exceptional. So localized measurements, way more generally now, you have, let's say, two systems, whatever dimension, can even go to more than two parties. But let's stick to two here. When you have all your resources here, let's say all in the phi+, so you have many E bits and bits of entanglement. You do one local operation here. You do one local operation here. You then get classical data, A and B. And this classical data code for the outcome of your non-local measurement. And there is a theorem again. First an example here. Let's do the example first. So we come back to these twisted bases, the one that we have already seen. So here, a way to measure that is to start again by adding some resource, so some E-bit here. Locally, Bob performs a Bell state measurement. So somehow you have kind of teleported these qubits to here, except that there is some Pauli distortion. You know that now this state here of these two qubits is the initial state here, but with this Pauli distortion on the second one. And the standard teleportation says then you have to communicate these two bits here in order to be able to correct that. But here we don't allow communication because Alice and Bob are kind of separated, or maybe even space-like separated. So what can we do? Well, what we can still do is that Alice, for instance, measure this first qubit here. And if it is a 0, then she knows it's one of these two. And so the second qubit she has to measure in the Z basis, that is written here. And if she finds her first qubit, this one, in the state, in the state 1, when she has to measure the second qubit in the plus minus basis, or what is often called the X basis, the horizontal basis. So you see that with the help again of a single EBIT, measurement of the twisted basis can also be localized, but not in an ideal way. And the full result on this study goes back to these gentlemen already quite some, more than 20 years ago. And they found a very impressive result, namely that all measurements in any dimension, any number of parties, they are always localizable. However, to do that, you need an unbounded, actually an infinite number of EBITs. To do it perfectly, you need an infinite number of EBITs. Infinite number of EBITs, that's not very physical. I can add a few qubits, I can maybe even add a large number of qubits, but I can certainly not add infinitely many qubits. So what we know, okay, maybe the summary of all that is that, so impossible measurements are localizable, so all measurements are localizable, so they are possible, contrary to what this terminology seems to imply. However, they cannot be ideal except the Bell state measurements. So now we want to use this kind of idea to start classifying joint measurements. Again, there is a continuous infinity of joint measurements. Let's try to classify that. And we want to classify them in function of the entanglement cost necessary to localize them. So you see, we found two examples of measurements, the Bell state measurement and this twisted measurement, where a single EBIT is sufficient to localize them. And then maybe the next step would be to have a few more EBITs. And so you can say the very simple measurement we can localize very simply. The next step will be a bit more complicated. The next step, again, a bit more complicated. But we get a physically very natural way of classifying joint measurements. Of course, if we have zero entanglement, so zero EBIT, then you can only localize product measurement, where Alice and Bob just do local measurements on their side. Okay, that's a bit trivial. But now, here, if we have a single one, and we assume the following protocol, which is exactly what I showed you. Now, Bob performs this Bell state measurement, of course, doesn't communicate to Alice his measurement outcome. And now Alice does more generally applies, so M denotes the unitary that maps the computational basis to the basis of our joint measurement. So she applies the inverse of this unitary and then performs a measurement in the computational basis. So she tries to undo as much as possible. Of course, she doesn't know the sigma b, so it's not always going to work. But we'll see that sometimes that works. And indeed, okay, you have then some equations that you would have to solve. Let me not show all the equations, but so you have M dagger, you have M that should be at the end just a permutation matrix. And indeed, not an ideal measurement, but there's a theorem that we have in this paper, that the lowest one here, which is coming out in PRX very soon, that tells you that with this kind of scenario, so a single EBIT as a resource, there are only two possible measurements that you can perform, either this twisted basis, which I showed you before, or the Bell state measurement. So these are possible, I showed that to you, but what the theorem says, there's nothing more you can do. So these are really the simplest measurements according to this classification. Now the next level is a bit more complicated. Here, how we prove it. I don't think I want to prove it here. It's anyway a bit complicated. It's not super complicated, but go and read the paper, you will find it. Okay, the next level of this hierarchy is again to start with this local Bell state measurement on Bob's side. Alice tries to undo as much as possible. But now instead of immediately trying to measure, she's going to use two more EBITs. And so she's going to use the first additional pair here to teleport these qubits to here with outcome A1, and these qubits to here with outcome A2. And now we want that A1, A2, and B collectively code for the outcome of this measurement. So some of these measurements are feasible, some are not. And again, there is some equations. Now it's getting a bit more complicated as an equation. And in this case, you can now do 3 more measurements. One, which is a well-known measurement, is called the partial Bell state measurement. Actually, in linear optics, one cannot do the full Bell state measurement, but this measurement that has 2 Bell states as eigenstate, and the 2 other eigenstates are product states. So this is typically a measurement that linear optics people can do, and which is called the partial Bell state measurement, and which can be localized with these 3 EBITs. There's another one which I'm going to introduce on the next slide, which is called the elegant joint measurement. You will understand soon why I name it elegant. And then there's another one, which is a kind of twisted Bell state measurement, which I'm not explaining here in details, but you can find all of these maybe in this other paper here. But you see, important, first of all, you have a very finite number of solutions, and these solutions are not new measurements. These are measurements that you find in the literature. People have thought of them because they are relatively simple. And so it seems that this way of classifying joint measurements is quite natural, because it provides natural measurements that people have already found useful for different applications. So what is this elegant joint measurement here? So I'm looking for 2 qubits. 2 qubits, non-degenerate measurements, that means 4 eigenstates. And I want now something with partial, right, that's state which have partial entanglement. And because the entanglement is partial, if it would be full entanglement, it would be equivalent to the Bell state measurement. If it has partial entanglement, then the local block vectors will have a finite length. And so these finite lengths, you have 4 of them. We want them to point towards the vertices of this tetrahedron, the regular tetrahedron here inscribed in the block sphere or the Poincare sphere, which is equivalent. So essentially, we are looking for states of that form, a superposition of a pair of qubits pointing in the jth direction, so the jth vertex, and minus that one, superposed with minus and plus that vertex. And of course, j runs from 1 to 4 in this example, with coefficients here. That's, of course, the square of the absolute value of these 2 coefficients should be equal to 1 for normalization purposes. And if you do the computation and you assume that these are real numbers, which is an assumption here, but if you do that and you impose now that this is really an orthonormal basis, so the scalar product of 2 of these should be 0 if they are different and 1 if they are identical, normalized, you get these numbers that come out here. And so here you have something which is kind of elegant, because, again, all the block vectors, they point towards these vertices of the tetrahedron. Okay, now you could do something and now try to combine this elegant joint measurement with what we've seen before. I see that I'm a bit late. With a triangle network. So if you do that, you get a very simple outcome here. Probability distribution by performing the same measurement everywhere and having singlets all the way in between. And this has now been proven very recently non-local. Okay, maybe the last thing. I'm sorry.
Yeah, it's okay. I mean, you can please continue. I mean, we cannot hear you.
Sorry, you cannot hear that. That's a pity. So, okay, let me stop here. So I'm sorry that you could not hear. So that was John Bell and his voice telling how and why he is a realist. Just wanted to share that video with you. I'm sorry that I don't know why exactly you could not hear it. Okay, but so there is this video of John Bell himself speaking about realism and non-realism. Okay, so but let me jump to the conclusion. Okay, I'm not going to repeat that, but these are the three ways beyond Bell inequalities which I presented today, and maybe you have some questions. I don't know exactly what is now the program and how much time we have for questions, but I'm certainly willing to answer a few questions if there are some. Thank you. I cannot hear you, but I see some people clapping, but I cannot hear anything.
Okay, so we will see if there are any questions. I don't know if people online who wants to ask. Are there some people online? Okay, just wait a minute. One question.
Yeah, this is about your second point, going beyond Bell's inequalities. This is about the network part.
Okay.
Can that be used to build a distributed quantum computer?
I guess yes. There is no reason. I mean, in quantum computers, you might really start with many independent pairs of qubits. That is certainly one possible architecture. And then you can entangle everything by these entangling measurements, these joint measurements. I guess maybe another question is also whether this is the most efficient way of doing of building a quantum computer. I don't think it's necessarily the most efficient. I was more thinking really in terms of quantum networks, between covering a country like India or Switzerland. There you will need a lot of sources of entanglement. And obviously, these sources will be independent. Maybe you even buy them from different providers. And then the question will be, at the end, this huge network that we would build in India or Europe, are they really quantum networks, or is that all fake? Similar as when we do a Bell inequality test, is that really quantum, or is that actually just classical with some hidden influences?
Follow.
Yeah, just a follow-up comment, but this could be a scalable quantum computer, though, because you can.
Yeah, indeed, because you could add more and more pairs of qubits each time with a source.
Yes.
But you need then a lot of joint measurements, of course. But I guess having a lot of measurements is anyway necessary for any quantum computer. It's a lot of gates somehow.
Yeah.
I agree.
Okay, thank you.
I didn't think much about that, but thank you for the suggestion.
Are there only questions online? Are there online questions? No. Okay, anybody else who wishes to ask a question? Okay, let me ask one question. So has anybody tried to test these Bell inequalities for network, this by non-locality?
Yes, there are some papers, not too many, but there are a few of these papers. It's a bit the beginning of this field of testing network non-locality. You see, it's a bit more difficult than the standard Bell because you have, of course, you must have at least 3 parties. And you need really to do not only measurements on one qubit, but on pairs of qubits. So you need to do joint measurements. And performing these joint measurements, for instance, this elegant joint measurement that has been performed now, but you need 2 CNOT gates to realize that. And so it's a bit more difficult experimentally. But yes, that can be done. And it's a research program which is ongoing now.
Okay. What is the question?
Hello. So can we apply the Bell measurement on Alice and Bob qubit, which are locally but on different qubit?
You mean Alice and Bob are they're at a certain distance and they have qubits of different sorts. You mean one is an atomic qubit and the other one is a photonic one? Is that the question?
Yes, yes.
Yeah, you can do that, indeed. That can be done. I mean, here on the theory, we've remained very abstract, so it's just qubits. How these qubits are implemented, again, in material or in massive particles or in photons or anything else, superconducting qubits, for instance, that is irrelevant at this level. Of course, it changes the experiment. I mean, there may be a lot of experimental challenges to measure jointly, a superconducting qubit and a photon, but there is nothing in the theory that prevents you from doing that.
Yes. Another question: Are Born rule are hold only for localized case?
Yeah, well, Born rule gives you the probability of measurement outcomes, and essentially it's very difficult to change the Born rule without activating signaling or activating non-locality and making it signaling. So the Born rule is something extremely basic and kind of necessary if you have these linear Hilbert spaces. And indeed, in our way of localizing measurements, you always recover the Born rule.
Yes, yes. Okay. Last question: that are you saying that the something superluminal effect exists till now experiment as far as we have done experiment in this regard?
Exactly. So this is still an open possibility. It's a kind of the last hope to make nature local, to go back to local physics. If there is nothing going on behind the scene, as John Bell used to say, then we have really to accept that nature is definitively non-local, which is which is certainly a bit my position. But at the end, it's not a matter of my opinion or your opinion or the opinion of anyone. It's something that we should investigate experimentally.
Can we realize tachyon in this way? Tachyon.
Yeah, tachyon. I'm not sure. I don't know exactly. The way I'm thinking of these hidden influences are going faster than the speed of light according to some privileged reference frame. Tachyons usually they're still are supposed to satisfy the Lorentz transformation. Simply they start faster than light, and after a transformation they're still faster than light. So here it's a bit a different philosophy, but I'm not sure I can really give you a complete answer, I'm afraid.
Okay, sir. Thank you. Thanks a lot. Wonderful lecture.
Thank you.
No other question. Okay. Can you just comment about this video which we couldn't see, that John Bell had this non-realist worldview?
This one.
Yeah.
So well, I mean, I guess you see the photo. So okay, that's John Bell in front of his blackboard at CERN, and you recognize now you have a source, you have then let's say a choice device that decides to send a photon to this analyzer or to that analyzer called A and A prime. So for me, that would be x equals 0, x equals 1 on one side, and similar for on the other side, again, measurement either this B or this B prime, which for me would be y equals 0 or y equals 1. And okay, and here you see again John Bell, probably a bit later, I would imagine. I'm not exactly sure. Again in his office, so I recognize that this is his office at CERN. And unfortunately, so here I could start the video again. I mean, it's not really a video, these are photographs. But there's a recording of his speech. I mean, it's a short speech, 1 minute or something like that, in which he explains that he is a realist, that he thinks that this is a natural thing, or the natural attitude of any physicist, that we are here to discover the world and not to invent the world. There's always these discussions about interpretation of quantum mechanics, and I thought it's nice to hear John Bell giving his clear view on that.
Okay, so thank you. Any other question? Oh, there is one more question. Last question, Mario.
Okay.
Sir, my question is regarding causality, and it is one of the backbones of relativistic theory of quantum mechanics. And given that causality is basically if two events in space-time are space-like separated, they cannot affect each other. But the non-local correlations, they simply violate that. So do we need to redefine causality, and how will that change the theory of relativistic quantum mechanics, if you can comment on that?
Okay, so to answer the last question, I cannot, because no one knows how to combine relativity and quantum mechanics. Now, do we need to change causality? I guess yes. I mean, I think you said it also. I mean, these quantum correlations that violate Bell inequalities between space-like separated parties requires a new form of causality. However, notice this is a kind of non-local, but also stochastic causality. So it's not that if I push here, something happens there. It's not by necessity. These are probabilities, and you have somehow probabilistic events at Alice and at Bob, and these two events are correlated according to quantum predictions. Somehow I often say that there's one random event that manifests itself at two locations. And because of this randomness, we cannot use these correlations to signal. So Alice cannot communicate to Bob, and Bob cannot communicate to Alice by merely using these correlations. So this is indeed something very special, and I would agree that this requires a new, that we revisit the concept of causality and enlarge it. Standard causality says that there is either direct causality, which I'm now doing. I'm causing something that you are hearing something at the other end of this communication channel. That's direct. And then there could be also a common cause, something that comes from a common past of you and me. And because of this common origin, we get also correlated. We see the same sun. And so, except for this time shift of, I think, 4.5 hours, we are also kind of correlated because we are on the same planet orbiting the same sun. And the sun acts as a common cause to you and me. But now, according to quantum mechanics, there is indeed something in addition to this direct cause and common cause source.
Okay, so I mean, thank you very much. So let's again thank Professor Gisin for a wonderful talk.
Thank you.
Okay, so thank you. Your wonderful talk, and I think all of us have learned something new. I mean, there are foundational questions which are still to be answered. Thank you very much.
Okay, thank you.
Thank you.
Bye-bye.
Bye-bye. Can you disconnect? Who have not seen quantum sensing lab, I think Tanmay is. So you have some of you who still wants to see. Tanmay work is still around. You can go to the lab and see. So first thing is I want to say, okay, I think talk a bit heavy, so I think perhaps next time we should do a better job so that most of you can benefit a bit. But I hope you have been exposed to something different. So you know some new areas where people are working on. Okay, maybe we'll have some ideas on that. Now I think I'm going for the center director.
I know that you for coming to this event. Very much enjoyed having you, and so happy that you could make and visit us. So what I'd like to say is that please keep in touch with us. They will be having events. Meet us, discuss with us about research, and get to know about opportunities in this field. To be having the courses not the embassy level yet, but we will have soon. So do keep in touch with us. Thank you again for coming.